Hi guys, probably the most common question in the tutorial session on Monday was from the exam question regarding the diving board. So I thought I might just take a little while to go through that step by step. So the question starts by asking from memory the reaction at one of these points. Now, first thing we need to do is we'll draw the diagram, which is already completed on the exam paper, and then set up some dimensions. So I think you just need to scale these from the paper. Now from memory that makes about 1/2 metre between the supports, and I think it's about 2 metres the length of the diving board from the first support. So from the notes, we engineers can write equilibrium equations, and we typically write these about Cartesian coordinates. So if we call this direction X, this direction Y, and then some direction that comes out of the page, we'll call that Z. So then we can write equilibrium equations such as the sum of the forces in the direction Y must equal to 0, and also the sum of the moments in the direction Z, so that's something that's twisting in this direction. Okay, so the diving board twisting about here causes an action that's defined about a vector going this way, so the sum of the moments in Z must equal 0. So it simply means if there's something that's rotating the diving board in this direction and the diving board is in equilibrium, then there must be an equal and opposite restraining force in this direction, in the opposite direction, stopping the diving board from moving, from becoming dynamic. Okay, so the question is about free body diagram. So a free body diagram is a rigid system. It's not a way for engineers to look at stresses, internal stresses in different types of elements, different types of materials. A free body diagram is simply a way of defining equilibrium and working out reactions at the boundary of the free body. So, to work out forces at C and D, first thing I need to do is to define the boundary of my free body. So I'm going to do this by marking a line through here. So this is essentially a box, and the only things that cross this box are the diver's feet, which is kind of irrelevant because the mass from the diver could be applied anywhere within the free body, but what we're saying is that at this point here there's a weight. Okay, so weight is the force as a result of having mass. So there's a weight here, which is a weight which is in the Y direction. So I think we've said that the person is 50 kilograms, which is 1/2 kilonewton. Now, you'll see that the only other 2 points that cross the free body diagram, the only 2 boundary conditions are there must be a reaction at C and a reaction at D. Okay. Now, we have 2 equations and essentially 2 unknowns. So the mathematicians will tell you that 2 equations and 2 unknowns is solvable. So we write the first equation, which is the simplest one. The sum of the forces in Y are equal to 0, and what that means is that the reactions must sum up to the weight in Y. Okay, so the sum of the reaction, so what they're saying is that the reaction in the Y direction at C plus the reaction in the Y direction at D must equal Wy. So that's great and obvious, but it can't solve the problem for us by itself because we have two unknowns and only one known. Okay? So we need another equation, and to do that we need to write an equation concerning the second known equilibrium, which is that the sum of the moments about z is equal to 0. Now there are two ways to do this, and I would encourage students to take moments about both point C and point D. I'm going to take moments about D. Okay, I'll put a little pin here, and I'm going to write equilibrium equations about that point. You could also choose point C. You could also choose this point here, but that point there is going to give you still two unknowns. Okay, so the reason why I choose C or D is that at C or D the lever arm is 0, so therefore that component of the equation is eliminated. Okay, so if I can write that out, what that's telling me is that 0.5 meters times the reaction in Y at C plus, if you like, 0 times the reaction in Y at D, which is just 0, equals 2 meters. Okay, the eccentricity from D to the point of the load, 2.0 times Wy. Okay, and that equation simply tells me that the reaction in Y at C is equal to 4 times the weight Y, which is 2 kilonewtons. So the question there, if the question asks for the force in the bolts at C, for example, the answer is 2 kilonewtons. Okay, and it's in tension. Alright. Now some of these questions are intuitive, so you can imagine if you were holding the structure in that point there and the bolt wasn't there, that point would be in tension. Okay, but you can also work out tension or compression from the sign conventions. Okay, by using the axes here. Okay, so substituting that back into the first equation here simply tells us that the reaction in Y at D is equal to negative 1.5 kilonewtons, which is in compression. Okay. Now if you repeat that process taking moments about C, you'll find that you get the same answer for C, irrespective of where you take moments about.